Suppose the answer is that there is better evaporation. Now what is the explanation for better evaporation?
Sir, the heat and dryness allow more evaporation.
Can you be a little more elaborate?
Sir, evaporation is the carry away of surface particles. The surface particles which have more heat.
Sir, when the temperature is hot, the surface particles have more energy and it's easier for them to escape. And since it is dry, they can occupy the space of the moisture in the air.
Sorry, the evaporation causes cooling.
Now, while discussing factors affecting evaporation, we discussed that an increase of temperature helps evaporation. Regarding dry, imagine there is some humidity already there. That means water particles are already there in the air. Won't it facilitate the reverse process also? And we don't want that for better evaporation. We don't want the reverse process. You don't want water particles in air to collide with the water surface and merge with that liquid part. You don't want that to happen. Clothes don't dry well in humidity because water particles that are present in the air collide with clothes and settle there only. You don't want that to happen for better evaporation. So on a humid day, cooler is not going to work well. It should be dry. Air should be dry. Moisture should be little. Humidity should be little. Any questions? Let me know.
Sir, in earthen pot there are very small tiny pores, so water can come out through that pores and they get evaporated. They use the heat from the surroundings and water inside the pot cool.
That's fine. Anybody else wanting to add something or make it sound a little different?
So during summer, the temperature is higher and it is easier for the surface particles of the water kept in the earthen pot to evaporate. As they evaporate, they take some heat along with them and cool the remaining water in the pot.
They take the heat from where?
From the surrounding water.
From the surrounding. Do all water particles have same chance of evaporating, or there are some water particles that have got greater chance of evaporating?
Sir, those
Confirm.
water particles which has high energy.
Right. Fine.
Sir, in a
Sir,
solid
The
more area is there.
surface area is more than this cup.
The evaporation is higher, so we can easily see the milk in the kept in saucer.
If area is higher, so what?
There are more surface particles which are able to evaporate.
Yes.
The area is higher, that means more surface particles with sufficient energy are able to leave the surface, thereby
Cooling
making it
Increasing
cool.
the temperature.
Yes. So average energy of the remaining particles is reduced. Average energy of remaining particles reduced means they are having lower temperature. That's fine.
Sir, cotton.
So cotton cloths. So cotton cloths.
Yes, I heard that, but I'm waiting for the explanation.
Sir, cotton
Sir,
being
cotton
a
has
good absorber
Cotton.
of sweat, they expose the sweat to the surroundings and it is easier to evaporate them.
Evaporate what?
Evaporate the
Sir.
sweat.
Would anybody else like to add something or change a little bit?
Sir, cotton has pores in it, so the water particles have more scope of escape. The sweat particles have more scope of escaping into the atmosphere. As they do so, they cool the body.
You mean if pores are made bigger, that will become better.
Yes, sir.
But I don't see huge holes.
Sir, the ones on
Sir,
the cloth
cotton
are
is good
enough.
absorber of sweat.
Yes. Cotton is a good absorber, generally speaking. Okay. Cotton is a good absorber. So what it means is that sweat will be absorbed and will be exposed to the surroundings better. So the particles of the sweat which are exposed to the surroundings better, the higher energy ones, they will escape. So evaporation will become better. We generally talk about three states of matter: solid, liquid, and gas. We deal with these as far as our day-to-day lives are concerned. But scientists have to deal with more, especially those who are working in certain areas. For example, somebody who is working on nuclear world, say fusion reaction, that person would be dealing with plasma also. So what is nuclear fusion and what is plasma? Basically, I'm talking about plasma, but to make it look related to something practical, there's a need to talk about fusion also. Normally when we talk about atoms, molecules, then the charges in them balance each other. Negative charges are equal to positive charges, so there is no net charge. When you comb and then you touch a piece of paper, then comb is able to attract it. But otherwise, you don't see it happening too often. Charges generally balance each other, but there are occasions where it does not happen. One charge becomes more than the other charge. Like if you have experienced, especially during winter season, that you touch some metal object, it could be the car's opening or it could be doors, knob, you suddenly feel some shock which remains for a very short period of time and goes away. It's not severe also. There are occasions where there is charge imbalance that is created. Inside the atom, it is believed that there are electrons which have negative charge. And these electrons are rather easily removed. So they can go from places to places, these electrons, by rubbing or by performing some other activities. Now imagine some object has got 100 electrons and 100 protons. Protons have got the positive charges. 100 electrons, 100 negative, 100 protons, 100 positive. Total is nothing, zero, zero charge. 100 protons, 100 electrons. But somehow you are able to remove 10 electrons from that thing. 10 electrons you are able to remove out of 100 electrons. 100 protons, 100 electrons, no charge. 100 protons, 90 electrons. There are 10 protons in excess. It's like saying plus 10 charge. I'm of course making it somewhat simple. So roughly say plus 10 type of charge is there on that thing because we have removed 10 electrons. How to remove electrons? I said by friction, rubbing, but there are other techniques also. Heating is another technique. Heating. Electrons should acquire so much of energy that they just jump away. 100 protons, 100 electrons, they are together, but electrons get some energy from outside and they jump away. They leave. One way to give this type of energy is heat. And electrons are able to jump away. Rubbing is another way. Heat is another way. Now imagine so many things are there having 100 protons and 100 electrons, so many of them. And everybody is losing 10 electrons, everybody. Maybe somebody 10, somebody 9, somebody 8, like that. So somebody has got plus 10 charge, somebody has got plus 9 charge, somebody has got plus 8 charge. Now, in sun, why so much of energy is present? Because of nuclear fusion reaction. What is nuclear fusion reaction? Some way of combination. Combination of what? Combination of something inside the atom. We will discuss more about atom later on, but right now you can think that atom is very small, but there is something inside the atom even much smaller than that, even significantly smaller than the atom. Inside the atom there is something. And that something is called the nucleus of the atom. It is not theory anymore. There are real bombs that are created by making use of that tiny thing inside the atom. The most powerful weapons are created using that thing, tiny thing inside the atoms. And not just weapons, there are power plants in our country also, in other countries also, that generate electricity by making use of that tiny thing inside the atom. Very tiny thing. That very tiny thing is called nucleus. It is so tiny that we can probably never see it. But not seeing does not mean not existing. You don't see when you press your remote what goes and hits your television. Isn't it? You don't see that. But doesn't it work? You press the on button and your television is switched on. Nothing else happens. Many things are studied by the effects that they create. We can't see them, but the effects that they create, on the basis of that we learn about them. Inside the atom itself is very, very, very small. There is something even much smaller present called the nucleus. Inside the sun, these small nuclei is a plural of nucleus. These small fellows are merging with each other and becoming bigger. Fuse, that's the meaning of the word fuse. You fuse two things, two small things you fuse. Two small nuclei you fuse. So fusion is what is going on in sun in a massive scale. And not just sun, any star that comes to your mind. Commonly speaking. Sun-like star, let me say. Nuclei are combining with each other. Now, we have also understood it and we are able to do the same thing on Earth. Or I should say something similar on Earth. So we are able to fuse the nuclei on Earth also. But we face a very difficult task when we try to do that. We can't have so much of temperature that Sun has. And the problem is that the nucleus of the atom is positively charged. Electrons don't live inside the nucleus. Negative charge, which is carried by electrons, that is outside the nucleus. Atom has got core. Its core, which is called nucleus, and core is positive. And then there are electrons surrounding that core, which are outside the nucleus. Inside the nucleus, you have nothing negative. You have got all positive. So the problem is that if you try to fuse two things which are both positive, you must have heard that positive charges don't like each other. Two protons don't like each other. One proton likes one electron, but one proton doesn't like other proton. One electron doesn't like other electron. Similar charges don't like each other. Similar charges don't like each other. Minus charge will repel minus charge. Plus charge will repel plus charge. And now nucleus is positive. Other nucleus is also positive. How will they make friends? For nuclear fusion to take place, they must come close and then combine with each other. And these two fellows are going to run away from each other. They are both being positive. Inside the Sun, story is different. It's a very high temperature. That high temperature is able to overcome this problem. That high temperature is able to overcome this problem. So, in Sun, this thing happens. If you want to do it on Earth, you should get such a high temperature that these two nuclei are willing to fuse, willing to come close. And when you do that, that temperature is so high that electrons which are outside the nucleus, they get so much of energy that they just say goodbye. They go out. So you have to get so much of temperature because you want that type of reaction to take place. And if you go for so much temperature, then electrons say goodbye. They go out. Which is no problem, by the way, for nuclear reaction. Nuclear reaction has nothing to do with electrons, this type of reaction. Now, I was saying earlier that if you have 100 protons and if you have 100 electrons, and out of 100, if 10 electrons go, then you have 100 protons and 90 electrons. You got plus 10 charge then. Now imagine the same situation here. You increase the temperature so much that enemies could come close, positive charges could come close. But while doing so, electrons manage to escape. That is another state of matter in which the electrons are running here and there. And what is without electrons, that thing is running here and there. They are sometimes colliding with each other, combining with each other, all those things happening. Normally, things are not without electrons. You hold anything, you will find huge number of electrons in that thing, anything that comes to your mind. You hold anything, you are holding huge number of electrons. But here, electrons say goodbye. They are going here and there, floating around. And because of such a high temperature, just imagine Sun's temperature near the Sun, and you will understand the whole thing. Imagine Sun's temperature near the Sun, not here. At that temperature, electrons get so much energy that atom cannot hold them. They just run away. So that's plasma. Plasma means normally you will find whether it's solid or liquid or gas. Everybody has got electrons in it. Everybody. Solid state, liquid state, gaseous state. But here, electrons are gone. So you are dealing with a sea of charges, electrons running here and there. Without electrons, that thing which was neutral is now positive. So those positive ions are going here and there. It's a sea of ions basically. Plasma is a sea of ions. In simplest language, in one sentence, plasma is a sea of ions. Charges, I should say. Sea of charges. Both types charges, positive and negative. And when I say sea of charges, it means electrons for negative and ions for positive, to be more specific. That makes it more specific. Sea of charges, which type? Negative are electrons, positive are ions. And they're all going here and there. So that is called plasma. It is not a theory. It's very much practical. There are several experiments that exist. Stars, there are just too many. Inside our galaxy itself, and just imagine beyond our galaxy. All these things are absolutely natural, but man can also do it. So I hope that would have made some sense, though it was much higher. I tried to make it simple, but still it was not so easy. Any questions about plasma, let me know.
Does only heat form plasma, or are there other methods to form plasma?
Well, you have to remove electrons. I can give you another example. Just hold on for a moment. Maybe I can find a picture. Well, even if I don't find the image, you certainly, I suppose, do understand what is a tube light. Certainly you understand that. Right? That tube light. Yes, I can see that private message. Just a moment. Okay, I will have to explain it without the image. No problem. You know what is fluorescent tube. So imagine some gas inside the fluorescent tube. Your ordinary tube light you can think of. So when you pass some current, then that can also give rise to ionization. And that can also lead to the formation of plasma. So that perhaps could be a simpler example. You can think of different fluorescent tubes, and inside them there is plasma present. Right? Yes, anything else? Or I move on to Bose-Einstein condensate. Bose-Einstein condensate. So what is this? This is much harder for you to understand and very hard to explain at this stage, because you're not yet exposed to many concepts like quantum number, etc. You will learn about quantum number in class 11, and you will be exposed to some half spin equal to half type of thing, electrons, spins, and all those things. Basically, if we make it really simple, then it has to do with very low temperature. You cool some gas, low density gas at very, very low temperature. If you ask how low, the lowest temperature is 0 Kelvin, at which we believe that no motion takes place, all vibrations stop. So near that range you have to go, that much of cooling. You can call it super low temperature. So take low density gas, cool it to that temperature. And something like this happens in very much layman type of language, that one atom, over it one more atom, over it one more atom, over it one more atom. Normally atoms are not like that. They are scattered or they are inside the molecules. Here one over the other. Basically condensation brings them close. Such a low temperature brings them close, gas particles close. Now you know that atmospheric air can be cooled to liquid at high pressure, low temperature, right? So you know that part. Here we are talking about really low temperature, very low temperature. In that they come so close that imagine one person is standing and at his place another person is also standing, same place. That is very hard to imagine. So imagine one atom, over it one more atom, one more atom, one more atom, they come so close, it looks like a super atom type of thing. So that's a very vague idea of Bose-Einstein condensate. And interesting thing is that it was predicted long time back, somewhere like 90 years ago it was predicted. At higher level, science comes quite close to maths, especially in some aspects. Science comes very close to maths at very high levels. If you look at Einstein's theory of relativity and many other things, highly mathematical, some things become. So Bose mathematically got something. Imagine getting some or thinking about some state of matter mathematically. So somewhere around 1920 he got it mathematically, and then he, I think, sent his work to Einstein, and then he translated it to German, I think, for some publication. And after several years, that fifth state was not obtained in the lab. Several years. It became a reality at a much, much later date. Now it's a reality. We know it is not just theoretical mathematics done by Bose. It's a real thing. Many things in science are like that. Many things that have been predicted earlier have yet to be proved experimentally. But we see the reality at this point of time. So think of it as something like a super atom. Okay? We are done with this topic, and no assignment for today. We stop now.